Hi, this is the final presentation of Group 18. Our group chose to optimize a desktop injection molding machine. This machine is used for small, low-scale injection molding parts. A user can input the material into the machine and it will be liquefied by heating and will be fed into the mold. And once cool, the parts will be ejected. And although the current production volume is limited, but we believe that the market size for this product is well above 50,000 units per year. Our primary customer is for hobbyists who wants to create injection molding parts at home, and their secondary customer are people who want to recycle plastic by creating the 3D printing filament. And here's the assembly CAD 3 views and the isometric view of our model. And here's the exploder view. And this is the functional analysis chart for our product. Here is the function component mapping matrix. And here's the remaining parts of the FCMM.
Our functional differentiation table FDT shows the functions that are the same for both customer groups and the differentiating function that is different for each customer group. Our differentiating function is to move plastic. This is different for each customer group. As for one, it is used to feed the injection molding machine, and for other, it's to feed the plastic to recycle to new filament for 3D printing. Our component commonality table CCT has columns for the platforms and the modules. The parts in the platforms column are from the same for both customer groups from the FDT, and the parts in the modules column are the parts from the differentiating factor in the customer groups from the FDT. These parts come from the functional component mapping matrix. Next, we have our common interface. This is the common interface where all the parts are the same for both variants, both for the injection molding machine and for the recycling into 3D printing filament machine. This interface is interchangeable and can be used for both variants.
Here's the quad chart of the primary variant.
Here we have two of our main variants for this injection molder. On the left, we have the main one that we've been talking about this whole time. That uses the two colliding plates to create a mold and feeds plastic into it using an auger. On the right, we have a similar feed system changing the extruder nozzle for a 3D printing filament size that feeds onto a motor-driven filament spool to recycle plastic into future 3D printing filament. On the next slide, we have our visual assembly diagram, where we can see that we do split at those extruder nozzles, since those will have to be different sizes for the two variants, which we can later change on the next slide to simplify out these two variants and how they're built, mainly separating out what's in the right side of the frame.
In the assembly analysis, we calculate the time taken for each part to be assembled. And we also calculate the total time and assembly efficiency about 3%. And we found the total time taken for assembly, the motor subassembly and the motor precision are taking a long time. And looking to our FCMM matrix, the motor precision only have one cross for feeding plastic. And for the quad chart, motor precisioner is on a low cost, low importance, which we consider elimination, and the motor assembly will be considered redesign for optimization. In design for manual assembly, we extend the plate in the motor mount to use the existing mounting point to reduce the part count and also reduce fasteners. And we also eliminate the motor precisioners, as mentioned before, also reduce the part count and reduce fasteners. And there will be negligible impact on the function. And for manufacturing cost, the assembly time reduced from 251.7 to 69.4, and also labor cost will be reduced correspondingly, and $1.69 reduced due to part elimination. And we choose another motor mount used in our module part. Basically, we change the structure to match the same motor mount used in our platform part. This provides hand and tool access to fasteners and reduce part variety. And we also narrow the rib features to match the motor width, which provide locating features. and we also add chamfers to edges. This can also provide locating features for fasteners. And regarding the impact on function, this provides a physical hand tool reach for fasteners after optimization, and also provide easier disassembling capability. And on the manufacturing cost, there can be potential increase in the cost due to the added features and more materials.
Now moving on to DFA redesign for automated assembly, we chose the extruder bearing assembly. This assembly was chosen due to its complexity and high functional importance to provide strength to the main extrusion screw. After determining the 5-digit automatic handling and 2-digit automatic insertion codes, we were able to estimate the assembly cost as $42.48 for the initial design and $16.56 for the redesigned assembly. This is a significant decrease in assembly costs, and this doesn't even include the decrease in material and part cost. As you can see, the original assembly consisted of 13 components and the new assembly only has 4. After inspection into the function and priorities of the original assembly, we found that a lot of the parts were too complicated and over-engineered for its function. Only one bearing is required that can be placed directly into the main plate. The new design overall reduces the part count, fastener count, minimizes turning over, and prioritizes Z assembly without impacting functionality and decreasing manufacturing costs.
For our first DFM part, our process selection is with this motor assembly and motor positioner mount. Here we can see that due to the thickness of this piece, sheet metal working is actually the best process to select for this.
For our first DFM redesign, we used the motor positioner from the process selection slide above, and using DFM Pro, identified 3 design guidelines to change. They were the minimum distance between the cutout holes for the outer holes and the inner holes, the cutout distance to the part edge, and then we addressed these by moving the outer holes in further from the edge and also shrinking the inner hole some. The cost went down from $1.32 to $1.17 per part. Although Hubs was not able to provide an instant quote for our sheet metal working part of it, was able to write a quote for additive manufacturing and 3D printing, which only fell in the batch size, so we thought that it would be a rough estimate of the cost. Our analytical method provided costs much lower than the Hubs method. This could be due to many factors, such as the batch size being far lower in the Hubs versus the analytical.
Here is our process selection diagram for a motor mount. As we can see here, die casting resulted in the best, with things that we would expect to match, like sand casting, dying out due to the overall mass. This piece is just simply too small. So die casting will be the best process for this.
Our second DFM redesign was done with the part above from the process selection slide. Using DFM Pro, we identified 3 key design guidelines of the wall thickness variation, uniform wall thickness in the middle, and the mode wall thickness. In order to mitigate these, we used draft angles and also decreased the wall thickness of the part, and the cost decreased from $1.67 per part to $1.49 per part. For our product service systems, PSS, material is the largest continuous cost. There's also plastic waste is a large issue, and this could affect globally. We can potentially reduce the quality of the product, and this allows the company to be involved in the life cycle of a product. The environmental benefits of this is the redesign can reuse plastic for making filament for 3D printers, and the original design allows certain types of plastics that can't be recycled traditionally to be used as well. This creates many customer benefits to reuse different plastics.
And to round out this presentation, we have our benefits from DFM/DFMA, which are the reduced assembly, manual assembly time through part consolidation. We saw the lowered costs in automated assembly and improved costs from changing the designs of the parts. These design changes simplified assembly and created better part geometries, although there are studies that could be done to validate the durability of these changes. Overall, the methods learned in this class were extremely useful in redeveloping a assembly like this. And our final design is more manufacturable and suited for high volume production.